Alright guys, so in this section we're going to be talking about some basic differentiation rules and rates of change. In the last section we discussed the formal definition of a derivative, taking the limit of that difference quotient and figuring out what the derivative of a function is, which as it turns out is also a function itself. But now instead of using the definition every time to find a derivative, we're going to start deriving some basic rules for differentiation that we'll use all the time. Okay, so first of all, we're going to have a word about notation here. You will see different types of notations, different textbooks, but we typically go back and forth between these two notations here. So this first notation with the apostrophe comes from Newton, and this other one here with the one that looks like a fraction, like a ratio, is Leibniz notation. But we will use these two notations interchangeably throughout the course. Okay, so our first rule here would be the constant rule, and this is a very straightforward rule. And by the way, guys, all the rules that we're going to be deriving here can be easily proven with just the limit definition of a derivative. Now, for the sake of time, we're not going to be proving all of them. We'll do maybe a couple just to give you the intuition, but you can do the rest as practice. But basically, that's all we have right now. We have the definition of the derivative, which is the limit of that difference quotient, and we can find any derivative with that, but that's a rather lengthy process. So here we have this first rule. The constant rule basically says, and I'm using Leibniz notation here, we're taking the derivative of a constant with respect to x, and x is in general is going to be our input variable. But if we just have a constant though, here c is just any real number, any constant here, this is going to be equal to 0. So a couple ways to see it. So intuitively, just think about a constant function, right? How does that constant function looks like? Well, if I was to graph here and say c is right here, you know that a constant function is just a flat horizontal line. Remember now we can think of the derivative as the slope of the tangent line. We discussed this in the previous section. So if we have a horizontal line here, we already know that the slope of any horizontal line is just 0. So intuitively, just thinking about the graph here, you can think of this derivative of a constant, and this will work for any constant here because it doesn't matter where c is, you're always going to get a flat horizontal line. At any point in this function, the slope is 0. So that's what that result is, that derivative of a constant is 0. Now, of course, we can prove this with the formal limit definition. And I'll do this one since it's very simple and very basic. It won't take too long. But all the rules that we're going to be deriving can be proven with that basic definition. So recall here our formal limit definition of the derivative. So let's say our function here, as we said, it's constant. So let's say it's equal to this c. Then the derivative of this function using the definition here would be limit, and remember our difference quotient here, as h goes to 0 of f of x plus h minus f of x over h. So let's go ahead and plug everything in and see what we get. Okay guys, so here we have it. The function at any input, doesn't matter what it is, x plus h or anything else, since this function is constant, is just c. So function at any input is c, so c minus c over h, and this is the limit of 0 over h as h goes to 0. But then 0 divided by anything is just 0. And we know that the limit of any constant, we already know that from last chapter, is just a constant. So the limit of 0 as h goes to 0 is just 0. And so this shows and proves that, in fact, the derivative of any constant is equal to 0. And again, this c was arbitrary, so it will work with any constant, right? If we want to do a quick example here, say f of x is equal to 12. So then the derivative, and this is Leibniz notation, would be 0. You can also say with Newton's notation, f prime of x is also equal to 0. So there's two different ways of showing the same thing, right? But then from now on, we don't have to use this lengthy definition to show or prove that, you know, the derivative of a constant function is just 0. We'll just know from now on, we'll just use that. And we'll add it to our bank of rules here. And we're going to keep adding and deriving more rules here that will help us find these derivatives quicker. Okay, so our next rule here is called the power rule, and it's called this way because we're taking the derivative of a power function here. Power function, we mean just x raised to some power, right? the derivative of x to the n is equal to n times x to the n minus 1. So it's basically like you brought this exponent to the front and then you kept the variable raised to the same exponent minus 1. Okay, so an example here would be if you have, say, f of x is equal to x cubed, and I mean it doesn't matter what power you have here. Now you're going to be able to find the derivative quickly with this rule. I'm going to use Newton's notation here. You bring the 3 to the front, keep the variable, and then the exponent will be 1 less than the one you had before. So 3 minus 1, this will be 3x squared. So that would be your derivative. So the derivative of x cubed would be 3x squared, right? And so forth. So notice how if we were to use the limit definition for the derivative, it would take us a long time just to get that. And so then from now on, we'll just use this rule. Okay, another quick example that you want to just know from now on would be if we have just a function equal to x, f of x equal to x, the derivative of this function would be, so if you apply the rule here, remember that x has a power of 1 understood there. So you, right, technically if you want to apply the rule, you bring the 1 down times x, 1 minus 1, but 1 minus 1 is 0. This 1 there, we can just omit it because it's understood. But this comes out to be x to the 0, which is just anything to the 0 is 1. So then that's one that you want to just know right away, right? F of x equal to x. So for that linear function, the derivative of x is just 1. So again, that comes straight from this power rule, but it's one that you may want to just know. Okay, so a couple other examples that are not so obvious where you can also use the power rule are the following. So this next example, you have 1 over x to the third power. Instead of having x cubed, you have the reciprocal of that. So how can we use the power rule here? Well, if we rewrite this function in the following way, since it's reciprocal, we can bring the x cubed to the top and change the sign of the exponent to a -3. Then now we can look at this 1 over x cubed as a power function here. So then, we have a negative exponent, but that's okay. This n could be really any number. And then we can now use the rule to find the derivative of this function. We bring the -3 to the front, x to the, and then here we gotta be careful. It's -3 minus 1 is always -1. So then we end up with -3x to the -4th. And then of course you can always rewrite this if you like in this way. You can bring that variable to the bottom with a positive exponent in the denominator there. The point is that you can rewrite it so that it looks like a power function and then use the power rule there. Okay. In the same way for this next example, you have a radical function here, and if you remember, we can write it radical. We can rewrite this function in exponential form here by putting in, again, this x has a 1 understood there. That would be the numerator of your exponent divided by the root of that radical, so that would be 1/5 in this case. So we can write this 5th root of x is the same thing as x to the 1/5, and we can now look at this power function and use our power rule to find the derivative of it. Okay, you bring the 1/5 to the front, keep that x there, and now it's 1/5 minus 1, which again, you'll do your calculation 1/5 x to the -4/5. Now you can rewrite this or leave it whichever way you want it, but this is 1/5. Notice how you can rewrite this exponential expression with a fractional exponent as a radical again. This negative brings it to the bottom here to make it positive, and then you can again leave it as a radical here. So different ways that you can do that, but the point is that you can use a power rule to quickly derive the derivative of these functions. Okay, so our next rule here is a constant multiple rule, and this one is pretty straightforward here. When we have a multiple or a constant multiplying a function, this constant can come outside of the derivative. Again, if you have a c, so the c here again is just a real number, any constant. C is a real number, and the derivative of a function that is being multiplied by a constant is equal to just the constant times the derivative of that function. Okay, so here's an example of the constant multiple rule. We have g of x is equal to 3x squared, and this 3 is acting as our constant here. So let's pretend our f of x here from the rule is x squared. We already know how to differentiate this function. It's a power function. Just from the previous rule, we can find the derivative of that. So applying this multiple rule, it says I can bring the constant out and multiply it times the derivative of that x squared function. So doing that, we have 3 times the derivative of x squared. We already know how to do that, and that is 2x. We multiply the 2 times the 3 to get the 6x. Okay, so here we have another rule, and this one again is another pretty straightforward rule, which says that when you have taking the derivative of a sum of 2 functions, or a difference, then that's equal to the derivative of the first one plus or minus, depending on which operation you're doing, the derivative of the second one. So you can find the derivatives individually and then add them or subtract them depending on what operation you're doing. So with these 4 rules that we've discussed so far, constant rule, the power rule, the constant multiple rule, and the sum and difference, you should be able to differentiate any polynomial function, because polynomial functions are formed by adding and subtracting a bunch of terms, and the terms look like a power function with a coefficient which is really just a constant in front of it, so that we can use this constant multiple rule and the power rule combined to differentiate any term of a polynomial. And of course, if we have just a constant, then we know that's equal to 0 for this derivative. And then the sum and difference rule would allow us to differentiate the whole polynomial for several terms. Okay, so here's an example here of a polynomial degree 5. But the derivative of this function would be equal to, we can take the derivative of each term at a time, because again, this sum and difference rule allows us to do that. We can do the derivative of each one. And notice how each term in this polynomial is really a power function times some constant in front, which we call the coefficients. So we can go ahead and do this. The derivative here of x to the 5th is 5x to the 4th minus 3. We bring the 4 down, 4x to the 3rd plus 2 times the derivative of x cubed. We've already done that one before. 3x squared plus, again, derivative of x, we said it was 1. And the derivative of negative 8 is just 0. Minus 0 plus 0, same difference. So then cleaning it up a little bit, simplifying our expression, we'll get 20x to the 4th minus 12x cubed plus 6x squared plus 1. And there it is. Again, another function as we expect, degree 4 now. And we're going to start seeing patterns here, how every time we take a derivative, you start seeing that as of a polynomial, we always go down a degree. A couple more derivatives that will come in handy, especially when we start dealing with coming handy later for trigonometric functions, are the sine and cosine functions. And we'll see the derivatives of the other ones as well later. But sine and cosine functions are 2 that we want to just go ahead and know. Their proofs are not as obvious as the other ones, but nevertheless, we can still use the limit definition of the derivative to show what the derivatives of sine and cosine are. They're going to be derived in a similar way. So I'll go ahead and show you the proof of the derivative of sine, and you can use the same idea to show the derivative of cosine as practice. But I think it would be worth going through the definition here for the derivative of sine here. And again, once we've seen how it's derived, we can just use it. It's very straightforward. We don't have to keep reproving it. So by definition here, the derivative of a function, our function here is sine of x. Using our definition from the previous section, we have that the derivative of sine x would be the limit as h goes to 0 of what? Our function, again, our function is sine of x. So let me rewrite the whole definition here. If you recall our definition of derivative, right? So now we're going to start plugging in what the function is here. So let's evaluate, and remember, we're still taking the limit as h goes to 0. F of x plus h, that would be sine x plus h minus sine of x. All of this divided by h. Now here is how are we going to simplify this? Because remember, the whole idea of the difference quotient is to try to get this h out of the way so that we can plug in the 0 in there. So how are we going to work this out? Well, here is where your trig identities will come in handy. If you recall your sum and difference identities, you should be able to expand this sine of x plus h. So let's go ahead and do that now. So if you recall, sine of sum of two angles here was sine of the first one times cosine of the second one plus cosine of the first one times sine of the second one. So this was an identity from your trigonometry course. And we have the minus sine x, still everything being divided by h here. So what do we do next? So we're going to try to move some things around and figure out if we can use some limits that we already know. Okay, so here we have it. All I've done is I moved this middle term here, wrote it here first. We're adding all these terms here so we can move them around. Move this one here, and then I took the other two, the first one and the third one here, and now notice that I have sine x on both terms, so I went ahead and factored that out. Put this one first. Matter of fact, I factor out the negative sine x, so I ended up with 1 minus this one has cosine of h there. And then I ultimately split these two terms now into two fractions. Since everything is under h, I can split them in this way with the purpose of seeing hopefully some limits that I'm already familiar with. If you recall here, this part, right, should look familiar to you from a previous section, and also this one there. Okay, so we already know properties of limits allows us to split these things into, I can take the limit of this minus the limit of that, granted these limits exist, and then I can further split the limit, these products, into the limit of cosine as h goes to 0. Now there's no h in cosine x or sine x, so those things are not being affected by the limit there. We can actually pull those out, but the ones that have an h happen to be those special limits that we discussed previously. So if you recall those special limits from a previous section, we had that this first limit, sine x over x as x goes to 0 is equal to 1. The second one, 1 minus cosine x over x is equal to 0 as x goes to 0. This first two come up and are proof for the derivative of sine. So here we have it then. The limit of this sine h over h as h goes to 0, as we know, is 1. And the limit of this 1 minus cosine h over h as h goes to 0 is 0, right? We've already proven these limits previously. So this sine x times 0, just this whole thing goes away. And cosine x times 1 is just cosine x. So this whole derivative is going to be equal to cosine x. So we've proven that the derivative of sine is cosine x. And in a similar way, you can prove that the derivative of cosine is equal to negative sine x. So be very careful there. If we do this whole process again for cosine x, there's going to be a negative in front of the sine there. Okay, so one last rule here for this section, guys, would be the derivative of e to the x, right? Our natural exponential function here. And this one is really nice here because it happens to be itself. The derivative of the function is actually equal to the function value. So you can think of it as this, remember, derivative means the slope of the tangent line. So the slope of the tangent line at a given point in the graph of e to the x is actually the same thing as the y value or the function value at that point. So this, as it turns out, is a very useful characteristic of this function. All right, guys, so we've seen a few rules that are going to help us find the derivatives of a lot of functions, a wide variety of functions, such as polynomial, exponential, and some of the basic trig functions as well, like sine and cosine. Now, we have seen how the derivative represents the slope of the tangent line, but it can also be used to determine the rate of change of one variable with respect of another. Right? There's several applications for this. Sometimes we refer to this as the instantaneous rate of change because we're talking about one instant in time. But again, as I've mentioned before, the derivative is going to take on different meanings depending on the field of where it's being used. So a typical example would be the rate of change of an object moving in a straight line. We can also talk about the position of, or the rate of change of a free-falling object that is under the influence of gravity. So for instance, here we have a position function of a free-falling object. The s represents the position at a given point in time. So it's going to take an input t for time, and it's going to evaluate this input and this function here, and it's going to give you the position at a given position height, since we're talking about a free-falling object at a particular time. Now, here for our purposes, since we're dealing with gravity here on Earth, this g is going to be a constant. It's going to be 32 feet per second square or 9.8 meters per second square, depending on what units you're going to be using. But typically, we use feet per second square. So if you plug that in, you can simplify this further. And v sub 0 or v null is the initial velocity of the object at the time of departure, and s sub 0 is the initial height of the object right before it moves. Given this function here, this position function, if we wanted to find the velocity of this object at any given point in time, t, that would be equivalent of finding the derivative. So if we're going to define the velocity function, it's going to be equal to the derivative of the position function. Now we can rewrite this position function here. I'm going to go ahead and plug in, so let's assume we're in feet per second square. Plug that in here. Since the acceleration of gravity is constant, we can go ahead and plug that in. All right, so now we can go ahead and find the derivative of this function and get that the velocity function is going to be equal, and again, we already know how to, using our rules here, we know how to, this is a polynomial here, a quadratic specifically, and we can go ahead and find the derivative, negative 16 times 2. Input here is t, so it's understood that we're taking the derivative with respect of t. This would be 2t plus, again, v0 and s0 are just constants, so treat them as constants there. This would be v0 times 1. Derivative of t is just 1. And since s of 0 is just a constant, that's 0. Okay. Finally, we get negative 32t plus v of 0. And this will be your velocity function at a given time t. So we will see several applications of this. And of course, in an actual application problem, you'll be given the velocity, the initial velocity and the initial height. So you'll have those constants. And now with the derivative, you're able to find the velocity of that object at that given time t. Not only the position, you have the position function, you can plug in your t in there and figure out what the position of the object is at that time. But now with the velocity, you can find also how fast it was going at that time t.